Space is tearing itself apart faster than physics says it should. We measure the universe expanding at 73 kilometers per second, but our best theories predict 67. That gap shouldn't exist. Scientists just declared this a crisis. Something fundamental is broken in our understanding of reality. We're about to journey through the measurements that don't match, the dark energy that might not exist, and the timescape where gravity bends time itself across cosmic voids. If you're ready to see how the universe's expansion is rewriting the laws of physics, hit that subscribe button. The mystery begins now. Two teams of scientists point their telescopes at the same universe and get two completely different answers. One team looks at ancient light from when the universe was 380,000 years old. They measure how fast space was stretching back then, run the math forward through 13.8 billion years, and arrive at a number: 67 kilometers per second faster for every 3.26 million light years of distance. That's the prediction. The math checks out. The models work perfectly, but here's where reality breaks the equation. Another team measures galaxies near us, relatively speaking. They watch exploding stars called supernovae. They track pulsing stars that brighten and dim like cosmic heartbeats. They calculate distances with incredible precision, and they arrive at a completely different speed: 73 kilometers per second per 3.26 million light years. 6 kilometers per second doesn't sound like much. Walk away from a friend and you're both still in the same neighborhood. But scale that difference across billions of light years, and you're describing two fundamentally different universes. One where expansion follows the rules we've built over a century of physics. Another where something invisible is pushing harder than it should. This is confirmed science, not speculation. Both measurements have been checked, rechecked, and verified by independent teams using different methods. The James Webb Space Telescope recently joined the hunt, and its sharp vision only made the problem worse. Webb confirmed that the local measurements are correct. The discrepancy is real. Think of it like two clocks in the same room showing different times. One reads 3 o'clock, the other reads 3:10. You check both clocks. Both are working perfectly. Both are measuring the same flow of time, yet they disagree. That's the universe we live in right now. The gap has been growing for over a decade. At first, scientists hoped measurement errors would explain it. Maybe the telescopes had subtle flaws. Maybe the math had hidden assumptions. But every new instrument, every refined technique, every careful analysis only confirmed the split. The universe expands at one speed when we calculate it from the distant past. It expands at a different speed when we measure it right here, right now. Nobody knows why. Some researchers think we're missing a piece of physics. Others wonder if gravity works differently on cosmic scales. A few suspect that time itself flows unevenly across space. What everyone agrees on is this: one of the most basic numbers in cosmology, the rate at which reality stretches apart, refuses to make sense, and the measurements just got more precise. The conflict isn't just about numbers on a page. It's about 7 billion years of cosmic history we might have completely wrong. When cosmologists look at the cosmic microwave background, they're seeing the universe as a baby. Light from that era has been traveling toward us for nearly 14 billion years. They measure the pattern of hot and cold spots, feed that data into their best models, and predict how fast the universe should be expanding today. The prediction assumes dark energy turned on about 5 billion years ago and has been pushing space apart at a steady rate ever since. Here's the gap. Local measurements suggest the universe is expanding 8% faster than those predictions allow. 8% across billions of years means something happened that our models don't account for. Maybe dark energy is stronger than we thought. Maybe it started earlier. Maybe it's been changing over time instead of remaining constant like we assumed. The Planck satellite gave us the baby picture. It mapped the ancient universe with extraordinary detail, confirming that space was once dense, hot, and remarkably smooth. Using the laws of physics we know, cosmologists evolved that early universe forward in time. They calculated how matter should clump into galaxies. They predicted how dark energy should accelerate expansion. Everything fit together beautifully, a coherent story from the Big Bang to today. Then astronomers measured the universe right now and found it running faster than the story predicts. Imagine watching a film of someone's childhood, then meeting them as an adult. Their childhood photos show a small, shy kid. But the adult standing in front of you is tall, confident, and nothing like the child photos suggested they'd become. Something happened between then and now that changed the trajectory completely. That's what we're seeing across 7 billion years of cosmic time. The early universe data says expansion should have accelerated slowly after dark energy kicked in. The late universe data says it's been accelerating faster. Both datasets are rock solid. Both have been verified independently. Yet they tell incompatible stories about the same stretch of history. Scientists have been searching for errors for over 10 years. They've analyzed telescope optics, questioned statistical methods, and re-examined every assumption. The answer keeps coming back the same. The measurements are correct. The universe genuinely appears to be expanding faster than physics predicts it should. This isn't a small discrepancy that might vanish with better instruments. Webb Space Telescope just added its voice to the debate with the most detailed observations ever made, and the tension only increased. We're not looking at measurement noise. We're looking at a genuine crisis in cosmology. Something is accelerating the universe more than our best theories can explain. But what comes next challenges everything we thought we knew about that acceleration. Scientists don't use the word crisis lightly, but that's exactly what they're calling it now. Dan Skolnick stood before the American Astronomical Society in January 2025 and made a declaration that sent ripples through the physics community. The Hubble tension, he said, is no longer just a tension, it's a crisis. The measurements had reached a level of precision where ignoring the problem became impossible. After a decade of hoping the discrepancy would fade with better data, the opposite happened. Better data made it worse. The term Hubble tension refers to this clash between what we observe and what we predict. Tension suggests discomfort, something that might resolve itself. Crisis suggests something broken, something that demands we rethink fundamental assumptions. That shift in language marks a turning point. Here's what makes it a crisis. The expansion rate of the universe, called the Hubble constant, is one of the 6 most important numbers in cosmology. It determines how old the universe is. It affects calculations about dark matter distribution. It influences our understanding of how galaxies form and evolve. Get this number wrong, and you get the entire cosmic story wrong. For years, scientists measured this number at around 73 using nearby galaxies and supernovae. Other scientists measured it at around 67 using ancient light from the early universe. A 6-unit gap might sound small, but it's roughly 8%. In cosmic terms, that's enormous. That's the difference between a universe that's 13.8 billion years old and one that's 12.8 billion years old. That's the difference between models that work and models that crumble. Multiple independent teams using completely different methods all confirm the same split. Hubble Space Telescope measurements give 73. Planck satellite measurements give 67. Webb Space Telescope joined in and confirmed Hubble's results. Gravitational lensing studies split the difference. Type 1, a supernova observations lean toward the higher number. Red giant star measurements lean slightly lower. Everyone is measuring carefully. Everyone is checking their work. Everyone is finding real answers. Yet those answers don't agree. Think of it like 5 witnesses describing the same car accident. All 5 are credible. All 5 saw clearly. Yet 3 describe a red car and 2 describe a blue car. Someone has to be wrong, but the evidence suggests everyone is right. That's impossible. That's a crisis. The scientific community spent the last decade searching for errors in measurement techniques. They wondered if dust between galaxies distorted the light. They questioned whether different types of stars behaved consistently. They re-examined every instrument and every calculation. Nothing explained the gap. Skolnick's team just published results using a new approach. They measured the distance to the Coma Cluster, a group of galaxies relatively close to Earth, with unprecedented precision. They used that measurement as the first rung on the cosmic distance ladder. The result? 76.5 kilometers per second per megaparsec, even higher than previous measurements. The tension just got tighter. This is what forces physicists to declare a crisis. When better measurements don't solve the problem but amplify it, something foundational must be wrong. Either our instruments are systematically lying to us in ways we can't detect, or our theories about the universe are incomplete. What if the force we've been blaming for the universe's acceleration never existed in the first place? Professor David Wiltshire from the University of Canterbury just published research that challenges one of cosmology's most fundamental assumptions. Dark energy, he argues, is a misidentification. We've been mistaking the uneven flow of time across space for a mysterious accelerating force. According to his team's analysis, we don't need dark energy at all. This is a theory, not yet confirmed, but it's backed by compelling evidence. The Standard Model says dark energy makes up 68% of the universe. It's supposed to be a constant anti-gravity force pushing space apart faster and faster. We can't see it. We can't detect it. We only infer it exists because galaxies appear to be rushing away from us at an accelerating rate. Scientists invented dark energy to explain that acceleration, but Wiltshire's timescape model offers a different explanation. His team analyzed light from distant supernova explosions with improved techniques. They found that the universe isn't expanding uniformly like we assumed. Instead, it's lumpy. Space stretches faster in vast empty regions called voids and slower in dense regions filled with galaxies. When you average out these different expansion rates without accounting for how lumpy the universe actually is, you get a false impression of acceleration. Here's the key insight from general relativity that makes this work. Gravity doesn't just bend space, it also warps time. Clocks tick slower in strong gravitational fields. A clock on Earth runs slightly slower than a clock in empty space. Scale that up to cosmic distances and time flows differently depending on where you are in the universe. Inside a galaxy cluster, where gravity is intense, time runs slower. In a cosmic void, where there's almost no matter, time runs faster. The difference isn't huge, but across billions of years it adds up. A clock in a void would measure billions of years more elapsed time than a clock in a galaxy cluster, even though both started ticking at the Big Bang. Now here's where it gets strange. When we observe distant galaxies, we're looking back in time. The light has been traveling for billions of years, but that light passed through regions where time flows at different rates. The stretching we see isn't necessarily acceleration. It might just be the result of light traveling through this lumpy, time-warped universe. Think of it like driving on a highway where speed limits change. In some sections you go 50 miles per hour, in others you go 70. If someone only measured your average speed without knowing about the varying limits, they might think you were accelerating when you were just following different rules in different zones. Wiltshire's model has been tested against supernova data, and it fits better than the Standard Model in some analyses. The team used data from over 1,000 supernovae and found that accounting for the universe's lumpiness removed the need for dark energy entirely. The apparent acceleration is an artifact of how we calibrate time and distance. This challenges 27 years of consensus. In 1998, two teams discovered that the universe's expansion was accelerating. They won the Nobel Prize in 2011 for that discovery. Dark energy became the centerpiece of modern cosmology. Now, some scientists argue we invented a placeholder for something we didn't understand. The debate is fierce, and the stakes are enormous. For a century, cosmologists assumed space was smooth like blended soup, but reality looks nothing like that. The equations we use to describe cosmic expansion date back to 1922. A physicist named Alexander Friedmann developed them based on Einstein's general relativity. These equations assume the universe is homogeneous and isotropic. Fancy terms meaning it looks the same in all directions and at all locations. Once you zoom out far enough, treat the universe like a featureless fluid, average everything out, and the math becomes manageable. That assumption worked beautifully for decades. But zoom in from those cosmic scales, and you see something completely different. Galaxies aren't scattered randomly like grains of sand. They cluster into groups. Groups cluster into superclusters. Superclusters form sheets and filaments that wrap around enormous voids. The universe looks like a sponge, with dense regions separated by empty bubbles millions of light years across. This is called the cosmic web, and it's confirmed by decades of observation. Here's why that matters for expansion. Empty voids and dense clusters don't expand the same way. Voids, filled mostly with dark energy and very little matter, expand faster. Dense regions, where gravity from visible and dark matter dominates, expand slower or even contract locally as galaxies pull together. Friedmann's equations can't handle this complexity. They assume you can blur all the details and treat the universe as uniform. But if different regions expand at genuinely different rates, averaging them together gives you the wrong answer. You might calculate an average expansion rate that doesn't actually describe what's happening in any particular place. Imagine trying to describe ocean waves by averaging the height of water across the entire Pacific. You'd get a number, sure, but that number wouldn't tell you anything useful about the actual waves surging and falling. The universe might be more like those waves than like a calm, uniform sea. Scientists have known about the cosmic web for decades, but assumed it didn't matter for expansion calculations. The thinking was that on large enough scales, the lumpiness averages out, and Friedmann's smooth universe equations work fine. Recent research suggests that assumption is wrong. The timescape model accounts for lumpiness directly. It tracks how different regions expand at different rates and how time flows differently in those regions. When you do that math, the apparent acceleration vanishes. What we interpreted as dark energy speeding up expansion is actually just the uneven, lumpy expansion of a structured universe. This isn't settled science yet. The standard model still fits most observations well, but the timescape model fits some datasets even better, and it does so without invoking mysterious invisible energy. The European Space Agency launched the Euclid satellite in 2023 specifically to test these ideas. Euclid is mapping the cosmic web in unprecedented detail, measuring how galaxies cluster and how voids expand. Data from Euclid should reveal whether lumpiness matters enough to eliminate the need for dark energy. Results are starting to come in now. NASA's Nancy Grace Roman Space Telescope, launching in 2027, will add even more precision. These missions could settle the debate within a few years. Either dark energy is real and we need to figure out what it is, or it's an illusion created by treating a lumpy universe as smooth. Both possibilities rewrite cosmology, just in different ways. A clock in empty space measures billions of years more than a clock inside a galaxy cluster, and that changes everything. Einstein's general relativity revealed something deeply strange about time. It doesn't flow at a constant rate everywhere. Gravity warps time. The stronger the gravitational field, the slower time passes. This has been confirmed in experiments on Earth. Atomic clocks at sea level tick slightly slower than atomic clocks on mountaintops because they're deeper in Earth's gravitational well. Scale that effect up to the universe and it becomes profound. Inside a galaxy cluster, where trillions of stellar masses pull on space, time runs slower than in the vast voids between clusters. The difference is tiny from moment to moment, but across 13.8 billion years, it accumulates into billions of years of difference. A clock that started ticking at the Big Bang and sat in a void would now read significantly more elapsed time than a clock that spent those eons inside a dense galaxy cluster. This is confirmed physics, not speculation. Time dilation is a direct consequence of general relativity. Now, here's why this matters for cosmic expansion. We measure the universe's expansion by observing light from distant galaxies. That light has been traveling for billions of years, passing through voids and clusters. But light doesn't experience time. It travels at constant speed, regardless of local time dilation. When we analyze that light to determine how much the universe has expanded, we're using clocks that ran at different rates depending on where the light traveled. Think of it like measuring the growth of a tree using photographs taken with cameras that had different shutter speeds. Some photos captured time normally, others captured it in slow motion. If you don't account for the different shutter speeds, you'll misjudge how fast the tree actually grew. The timescape model takes time dilation seriously. It doesn't treat the universe as a uniform blob where time flows the same everywhere. Instead, it tracks how time flows differently in voids versus clusters. When you account for these variations, the expansion history looks different. What appeared to be acceleration might just be our misunderstanding of how to compare clocks across cosmic distances. In a void, where almost no matter exists, time runs faster. The expansion of space also happens faster because there's less gravity to slow it down. In a cluster, gravity is intense, time runs slower, and expansion is suppressed. We live in a moderately dense region, somewhere between these extremes, and we're trying to make sense of light that traveled through all of them. The math gets complicated quickly, but the core idea is simple. If time doesn't flow uniformly, then using a single cosmic clock to describe expansion is wrong. You need different clocks for different regions, and you need to account for how those clocks relate to each other. Wiltshire's team calculated what the universe's expansion should look like when you properly account for time dilation across voids and clusters. The result matches observations without requiring dark energy. The apparent acceleration is real in the sense that we genuinely observe it, but it's not caused by a mysterious force. It's caused by comparing measurements made with clocks that weren't synchronized. This is still being tested. The predictions differ slightly from standard models in ways that future observations should be able to confirm or rule out. Euclid and Roman telescopes will map enough of the cosmic web to test whether time dilation in voids matters as much as the timescape model suggests. If the model holds up, dark energy was the wrong explanation for 27 years. But there's more to the story. What we see when we look at the universe might be fundamentally misleading. Light takes time to travel. When we observe a galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago. That galaxy looks distant because its light has been stretched by the expansion of space during its journey to us. The amount of stretching tells us how much the universe expanded during that time. At least, that's what we thought. But here's the problem with that interpretation. If time flows at different rates across the cosmic web, then light traveling through voids experiences less time passage than light traveling through clusters. The stretching we measure depends on how long the light traveled, but measuring that duration requires knowing which clock to use, a void clock or a cluster clock. Standard cosmology uses a single universal time. It assumes we can talk about the age of the universe as if there's one cosmic clock ticking uniformly everywhere. That makes calculations simple, but it might be wrong. If different regions genuinely experience different amounts of time since the Big Bang, then the concept of a single cosmic age breaks down. The timescape model describes this with a term called kinetic energy of expansion. In simple terms, different parts of space are expanding with different amounts of energy. Voids expand vigorously. Clusters expand slowly or not at all. When you try to average these different expansion rates to get a single number for the Hubble constant, you create an illusion. Think of it like averaging the temperature of a room that has a fireplace at one end and an open window at the other. You might calculate an average of 70 degrees, but no part of the room is actually 70 degrees. Near the fireplace, it's 90. Near the window, it's 50. The average is real mathematically, but meaningless physically. That's what might be happening with cosmic expansion. We calculate an average expansion rate, interpret it as acceleration caused by dark energy, but the average is misleading. The universe isn't accelerating uniformly. It's expanding unevenly in a complex pattern we've been mistaking for something simpler. Light from distant supernovae travels through this lumpy structure. Some light paths cross more voids, some cross more clusters. The stretching we measure depends on the specific path each light beam took. When we assume all paths are equivalent because space is uniform, we introduce errors that look like acceleration when they might just be path differences. This is incredibly difficult to test because we can't replay cosmic history with different assumptions and see which matches reality better. We only get one universe to observe, but we can test the models against different datasets and see which makes better predictions. So far, the Timescape model performs well when tested against supernova data. It predicts the brightness and distance relationships we observe without needing dark energy. The standard model also fits the data, but requires invoking an invisible force that makes up more than 2/3 of the universe's energy budget. Occam's razor suggests choosing the simpler explanation when both fit the evidence. But here, simple is debatable. The Timescape model eliminates dark energy, which sounds simpler, but it requires tracking time dilation and varying expansion rates across cosmic structure, which sounds more complex. The true test will come from mapping the cosmic web precisely enough to measure whether voids really do expand faster in the way the model predicts. We're close to having that data. Within a decade, we'll know whether the cosmic web is playing tricks on our measurements. The force we thought was constant might have been evolving all along. Dark energy, spectroscopic instrument known as DESI, spent years mapping 15 million galaxies. The project aimed to measure how dark energy has affected the universe over the past 11 billion years. In April 2024, the team released their first results, and they contained a surprise that has physicists rethinking everything. Dark energy appears to be changing over time. This is still preliminary, not yet confirmed beyond doubt, but the evidence is strong enough to take seriously. The standard model treats dark energy as a cosmological constant, a property of space itself that never varies. Empty space has a fixed energy density, and that energy pushes space apart at a steady rate. This assumption made calculations elegant and matched observations reasonably well for 2 decades. DESI data suggests something different. When the team analyzed how galaxies cluster at different cosmic ages, they found hints that dark energy was stronger in the distant past than it is today. The effect is subtle, but if confirmed, it means dark energy is dynamic, not constant. Think of it like wind speed. You might measure wind blowing at 10 miles per hour and assume it's constant. But if you check historical records, you might find it used to blow at 15 miles per hour and has been gradually slowing down. That changes how you predict future conditions entirely. If dark energy is weakening, the universe's expansion might be slowing down rather than speeding up. That flips the story we've been telling. For 27 years, we thought the universe was accelerating faster and faster toward an eventual heat death, where everything becomes cold, dark, and infinitely separated. But if dark energy is fading, acceleration might stop. Expansion might even reverse. The implications are staggering. A reversing expansion leads to a big crunch, where the universe collapses back on itself. Galaxies would rush together instead of apart. Space would shrink instead of stretch. Everything that expanded since the Big Bang would contract back to a point. That's the opposite of the future cosmologists have been predicting. DESI measured this by looking at baryon acoustic oscillations, a fancy term for a characteristic distance between galaxies that acts like a cosmic ruler. By measuring how this distance has changed over billions of years, they reconstructed the expansion history. The pattern they found doesn't match a constant cosmological constant. It matches a varying dark energy better. This could explain the Hubble tension. If dark energy behaved differently in the past than it does now, then predictions based on the early universe would naturally disagree with measurements of the current universe. The mismatch wouldn't be an error. It would be evidence that dark energy evolved. But here's where it gets complicated. Other measurements don't show the same variation. Planck satellite data fits a constant dark energy well. Supernova observations are consistent with constant acceleration. DESI's hint of change is statistically significant but not overwhelming. It could be a real signal or a statistical fluke that will disappear with more data. The team is continuing observations. By 2027, they'll have enough data to confirm or rule out evolving dark energy with much higher confidence. Other missions like Euclid and Roman will add independent measurements. Within a few years, we'll know whether dark energy is truly changing or whether DESI saw noise in the data. If it's changing, the next question becomes why? What physical process would cause the energy density of empty space to vary over time? We don't have good theories for that. It would require new physics beyond the standard model. The stakes keep rising with every measurement. New research suggests expansion might have already begun to decelerate. Young Wook Lee from Yonsei University in South Korea led a team that analyzed decades of supernova data with a fresh approach. Their findings, published recently, claim the universe has already entered a phase of slowed expansion. If true, this marks one of the most important discoveries in cosmology since the detection of acceleration itself. This is a new theory, not yet widely confirmed, but it challenges the core narrative of modern cosmology. Standard thinking says dark energy started dominating about 5 billion years ago and has been accelerating expansion ever since. The acceleration should continue indefinitely, eventually ripping apart galaxies, solar systems, and even atoms in a scenario called the Big Rip. Or expansion should continue forever at an accelerating rate, leading to heat death where the universe becomes cold, dark, and empty. Lee's analysis suggests that's wrong. According to their calculations, expansion already peaked and is now slowing down. We're past the maximum acceleration phase and entering deceleration. Dark energy, if it exists, is losing its battle against gravity. Here's what that means. Gravity tries to pull matter together, slowing expansion. Dark energy pushes space apart, speeding expansion. For most of cosmic history, gravity dominated, slowing the expansion that started with the Big Bang. Then dark energy took over, and expansion accelerated. Now, according to this research, dark energy is weakening and gravity is winning again. Think of it like throwing a ball upward. Gravity slows the ball until it stops and falls back down. The universe's expansion might follow a similar pattern. It exploded outward, slowed down, temporarily accelerated when dark energy kicked in, but is now slowing again as dark energy fades. If this continues, expansion could stop entirely, then reverse. Galaxies would start moving toward each other instead of away. Space itself would contract. Over hundreds of billions of years, the universe would collapse back into a big crunch, the opposite of the Big Bang. This ties into the DESI findings about evolving dark energy. If dark energy is getting weaker over time, then deceleration is exactly what we'd expect to see. The universe accelerated when dark energy was strong. Now that it's weakening, acceleration is giving way to deceleration. But other scientists are skeptical. The evidence for deceleration isn't overwhelming yet. The measurements are subtle and depend on how you interpret complex data. Different analysis methods give different results. Some show continued acceleration, others show slowing. The uncertainty is still too large to declare victory for either side. What makes this so important is the fate of everything. If acceleration continues, the universe ends in cold isolation. If deceleration continues, the universe ends in a fiery collapse. These aren't just abstract possibilities. They're the actual futures awaiting all matter, energy, and structure in existence. Webb Space Telescope, Euclid, and Roman will help settle this debate. They'll measure the expansion rate at different cosmic ages with unprecedented precision. If expansion really is slowing, these instruments will detect it clearly. If it's still accelerating, the data will show that too. We're living at a unique moment in cosmic history. For the first time, we have instruments powerful enough to measure whether the universe's fate is isolation or collapse. The answer could come within the next 5 years. Until then, both futures remain possible. If expansion reverses, everything that exists will be crushed back into a single point. Imagine watching a film of the universe's history in reverse. Galaxies rush together instead of apart. Stars collide and merge. Gas clouds compress and heat up. Space itself shrinks, forcing everything closer and closer together. That's a big crunch, the mirror image of the Big Bang. This is a theoretical possibility, not a confirmed prediction, but recent findings make it worth considering seriously. For decades, cosmologists assumed the universe would expand forever. Matter spreads out, stars burn out, black holes evaporate, and everything fades to cold darkness. That future seemed certain after the discovery of accelerating expansion in 1998. Dark energy appeared unstoppable, destined to push everything apart for eternity. But if dark energy is weakening, that future changes. Gravity never stops pulling. Once dark energy fades enough, gravity takes over and reverses the expansion. The universe would contract slowly at first, then faster and faster as matter drew closer together and gravitational pulls strengthened. Here's what that process would look like across unimaginable timescales. First, over hundreds of billions of years, distant galaxies would stop receding and start approaching. The redshift we currently observe, where light from galaxies stretches toward red wavelengths because they're moving away, would reverse to blue shift as they move toward us. The night sky would gradually brighten as galaxies crowded together. Eventually, galaxy clusters would collide. Stars would pass near each other, disrupting planetary orbits. Some worlds would be flung into interstellar space. Others would spiral into their stars. The organized structure of galaxies would break down into chaos as gravitational interactions intensified. As contraction continued, gas clouds between galaxies would compress and heat up. The universe would get hotter instead of cooler. Background radiation would shift from the cold microwave frequencies we measure today toward infrared, then visible light, then ultraviolet, then X-rays. Space itself would become an oven. Stars would merge into larger, hotter objects. Planets would vaporize. Matter would break down into plasma as temperatures soared. Eventually, even atoms would be torn apart by the extreme energy. The universe would return to conditions like those moments after the Big Bang, but in reverse. Finally, all matter, energy, and space would converge into a single point of infinite density. Time itself would end, along with everything else. That's the big crunch. This scenario depends on dark energy continuing to weaken or disappearing entirely. If dark energy remains even slightly positive, expansion continues forever, and the big crunch never happens. The current evidence for weakening dark energy is intriguing, but not definitive. We need more data. Some physicists find the big crunch appealing because it suggests the universe might be cyclic. A big crunch could trigger another Big Bang, restarting cosmic expansion with fresh conditions. The universe might go through endless cycles of expansion and contraction, each cycle lasting hundreds of billions of years. Other physicists think the Big Crunch is unlikely because measurements still favor continued expansion, just at a slowing rate. The universe might coast to a stop, asymptotically, never quite reversing but never expanding much further either. The only way to know is to keep measuring. Track the expansion rate over the next decade. Watch how it changes. See if deceleration continues or if acceleration reasserts itself. The answer will tell us the ultimate fate of everything that exists. And that answer is coming soon. Before the dark energy we know, there might have been another force that appeared for an instant and vanished forever. Physicists at MIT recently proposed something radical. What if dark energy existed twice in cosmic history? Once in the universe's first moments, then again billions of years later. The early version appeared for a fraction of a second, affected the infant cosmos, and disappeared completely. The late version is what we observe today, driving current acceleration. This is a speculative theory meant to solve multiple problems at once. The theory addresses two major mysteries. First, the Hubble tension, where measurements don't match predictions. Second, the unexpected abundance of bright galaxies seen by James Webb Space Telescope in the very early universe. Standard models predict far fewer large bright galaxies should have formed so quickly after the Big Bang. Yet Webb keeps finding them. Early dark energy would solve both problems if it existed. Here's how it would work. Imagine a force that turned on when the universe was incredibly young, perhaps when it was less than a few 100,000 years old. This force would be similar to dark energy, but temporary. It would push space apart briefly, accelerating expansion during a crucial period. Then it would shut off completely, leaving no trace except its effects on the universe's structure. This burst of acceleration would change how matter clumped together in the early cosmos. It would allow density fluctuations to grow faster, seeding the formation of galaxies earlier than standard models predict. More early galaxies means more bright galaxies visible to Webb, matching what we actually observe. Early dark energy would also affect the expansion rate in a way that resolves the Hubble tension. If the universe expanded faster than usual for a brief early period, then predictions based on the cosmic microwave background would need to be adjusted. The adjustment would bring those predictions closer to the higher local measurements we observe today. Think of it like a car that briefly shifts into a higher gear during part of the journey. If you only measure average speed at the beginning and end, you'll misjudge the total travel time unless you account for that gear shift. Early dark energy would be cosmic history's gear shift. The challenge is explaining where this early dark energy came from and why it disappeared. Dark energy today appears to be a property of space itself, something that doesn't decay or change much over time. Early dark energy would need to be something different, perhaps a field that only existed under extreme conditions present in the infant universe. Some theories propose a scalar field, similar to the inflaton field, thought to drive cosmic inflation, but distinct from it. This field would have high energy when the universe was young and dense. As space expanded and cooled, the field would roll down to lower energy states, eventually vanishing entirely. The math works in principle, but there's no direct evidence yet. The theory makes predictions that future observations should be able to test. Detailed measurements of the cosmic microwave background might reveal subtle imprints left by early dark energy. Continued observations of early galaxies by Webb will either support or contradict the prediction of enhanced early structure formation. If early dark energy existed, it would add a new chapter to cosmic history. The universe would have experienced three distinct phases of expansion. First, inflation, the exponential burst right after the Big Bang. Second, early dark energy, a temporary acceleration during the first 100,000 years. Third, late dark energy, the current acceleration that started billions of years ago. Each phase would have shaped the cosmos differently, leaving its signature in the structure we observe today. The evidence is building, but proof remains elusive. Light from opposite sides of the universe looks identical, but those regions should never have communicated. When scientists mapped the cosmic microwave background, they found something remarkable. The temperature is nearly uniform across the entire sky. Whether you point your telescope north, south, east, or west, you measure almost exactly 2.7 Kelvin everywhere. Tiny variations exist, but they're less than 1 part in 100,000. The universe looks extraordinarily smooth. Here's why that's bizarre. Light has a speed limit. Nothing, not even information, can travel faster than light. Since the Big Bang happened 13.8 billion years ago, light has only had 13.8 billion years to travel. That means any given region of space can only have communicated with other regions within 13.8 billion light years. That distance is called the cosmic horizon. When we look at opposite sides of the sky, we're seeing regions separated by far more than that. Those regions are so distant that light from one could never have reached the other in the age of the universe. They're beyond each other's horizons. They're causally disconnected. Yet somehow, they have the same temperature. Think of it like two strangers on opposite sides of Earth who have never met, never communicated, and don't know the other exists. Yet they both choose to wear the exact same outfit on the same day. That's suspicious. Something must have coordinated them, even though they've never been in contact. The universe faces the same puzzle. How did opposite regions end up with identical temperatures if they could never exchange energy or information? What coordinated them? Standard Big Bang theory has no answer. If the universe simply expanded from a hot, dense state without any special early phase, then different regions should have different temperatures. There's no mechanism to make them uniform. The smoothness we observe shouldn't exist. This is called the horizon problem, and it troubled cosmologists for decades. Cosmic inflation provides the solution. If the universe underwent a period of exponential expansion very early in its history, before the cosmic microwave background formed, then regions that are now separated were once much closer together. They were within each other's horizons back then. They had time to exchange energy and reach the same temperature. Then inflation blew them apart. Space expanded so rapidly that regions which were once in contact got stretched to opposite sides of the observable universe. They look disconnected now, but they share a common history from before inflation. Imagine blowing up a balloon. Draw two dots close together on the deflated balloon. As you inflate it, those dots move apart, eventually ending up on opposite sides. Someone looking at the inflated balloon might think the dots were never connected, but they were close together before the expansion. That's what inflation does to the universe. It takes a small, smooth patch of space where everything reached equilibrium, then expands it to cosmic size. The smoothness is real, but it's not mysterious. It's just the remnant of a time before inflation when everything was in contact. Inflation solves the horizon problem elegantly. The universe isn't smooth by accident. It's smooth because it started from a tiny region that had time to equilibrate before inflating to cosmic scale. But inflation itself raises new questions. The universe is flat to incredible precision, but the odds of that happening naturally are essentially zero. Space can have curvature, just like surfaces in everyday life. A sphere is positively curved. A saddle is negatively curved. A plane is flat, with zero curvature. General relativity says the universe's overall geometry depends on its density. Too much matter, and it curves into a sphere. Too little, and it curves into a saddle. Exactly the right amount, and it stays flat. Here's the problem. The right amount is incredibly specific. Even tiny deviations from that critical density early in cosmic history would have grown enormous over time. If the density was slightly too high, the universe would have collapsed back on itself billions of years ago. If slightly too low, it would have expanded so fast that no galaxies could ever form. Measurements show the universe is flat to better than 1% accuracy. That means the density is at or incredibly close to the critical value. For the density to be this close to critical now, it must have been absurdly close to critical in the early universe. We're talking about precision to 1 part in 10 to the power of 62. Think of it like balancing a pencil on its tip. If the pencil is even slightly tilted at the start, it falls over immediately. For the pencil to still be balanced billions of years later, it must have started perfectly vertical to impossible precision. That's the flatness problem. Why would the universe start with exactly the right density? What mechanism fine-tuned it so precisely? Standard Big Bang theory offers no explanation. It's just an incredibly lucky initial condition that we have to assume without justification. Cosmic inflation solves this problem too. During inflation, space expanded by a factor of at least 10 to the power of 26. That's a 1 followed by 26 zeros. Any curvature that existed before inflation got stretched flat by this enormous expansion. Imagine drawing a circle on a balloon. then inflating the balloon to the size of Earth. The circle would look flat because the curvature got diluted over such a vast area. You'd need incredibly precise instruments to detect any remaining curvature. That's what inflation did to the universe. Any curvature that existed before inflation became undetectable after inflation. The universe appears flat today, not because it started with a miraculously special density, but because inflation stretched it flat regardless of how it started. This makes flatness generic rather than special. Any universe that undergoes inflation should look flat afterward. The fine-tuning problem disappears because inflation naturally drives the geometry toward flatness. But inflation creates its own fine-tuning problems. What triggered inflation? Why did it last long enough to solve the flatness and horizon problems, but not so long that it erased everything? What stopped inflation and allowed normal expansion to resume? These questions remain unanswered. Some physicists argue that inflation just trades one set of problems for another. Instead of explaining why the initial conditions were special, we now have to explain why inflation happened at all and why it had the right properties to produce our universe. Others counter that inflation is a better explanation because it's a dynamic process that evolves according to physical laws, rather than just asserting special initial conditions without justification. Inflation is testable in ways that initial conditions aren't. The debate continues. But most cosmologists accept inflation as the best explanation we have for the universe's flatness. The alternative is accepting an absurdly unlikely coincidence. And coincidences like that beg for better explanations. Space expanded by a factor of 1 trillion trillion in less than a trillionth of a second. Cosmic inflation is one of the most extreme events ever proposed in physics. In a time interval shorter than a blink, the universe grew from subatomic size to something cosmically vast. The expansion rate during inflation was so fast that space itself stretched faster than light speed. This doesn't violate relativity because space can expand at any rate. Only objects moving through space are limited to light speed. Here's what that expansion means in concrete terms. Before inflation, the observable universe was smaller than an atom. After inflation, it was larger than a grapefruit. That might not sound like much, but the expansion factor was approximately 10 to the power of 26. That's the number 1 followed by 26 zeros. For comparison, the expansion from the end of inflation to today has only been about 10 to the power of 3, a factor of 1,000. Inflation crammed most of the universe's expansion into a tiny fraction of a second. Everything since has been coasting. What drove this exponential expansion? Physicists propose a field called the inflaton, similar to other quantum fields but with unusual properties. The inflaton field had high energy in the early universe. That energy behaved like negative pressure, pushing space apart rather than pulling it together like normal matter. Think of it like a compressed spring. The spring has stored energy that wants to expand outward. The inflaton field was like that, except instead of pushing matter apart, it pushed space itself apart. And unlike a normal spring that weakens as it expands, the inflaton field maintained constant energy density, even as space grew. More space meant more total energy, which drove even faster expansion. This is called exponential growth. Each moment, space doubles in size, then doubles again, then again. Doubling repeatedly leads to explosive growth. In about 100 doubling times, something grows by a factor of 10 to the power of 30. Inflation achieved this in a fraction of a second. Eventually, the inflaton field decayed. It transitioned from high energy to low energy, releasing its stored energy as ordinary matter and radiation. This process, called reheating, filled the universe with the particles that eventually formed atoms, stars, and galaxies. The exponential expansion stopped at normal. Slower expansion took over. Inflation explains more than just the horizon and flatness problems. It also explains where the tiny density variations came from that seeded galaxy formation. During inflation, quantum fluctuations in the inflaton field got stretched to cosmic size. These fluctuations created slightly denser and less dense regions in space. After inflation ended and matter formed, gravity pulled matter toward the denser regions. Over billions of years, those tiny variations grew into galaxies and galaxy clusters. The structure we see in the universe today traces back to quantum fluctuations during inflation. This is a remarkable connection. Quantum mechanics governs the behavior of subatomic particles. Cosmology governs the behavior of the entire universe. Inflation links them. The largest structures in existence originated from the smallest quantum jitters, magnified by inflation to astronomical scales. The theory makes predictions that can be tested. Inflation should have produced gravitational waves, ripples in space-time itself, along with the density fluctuations. Detecting these primordial gravitational waves would confirm inflation directly. Several experiments are searching for them now. The search continues, and with it, our understanding of how the universe began. The first inflation model broke physics in a way that nearly killed the theory. When Alan Guth proposed cosmic inflation in 1981, he recognized a fatal flaw in his own idea. The model solved the horizon and flatness problems beautifully, but it failed to explain how inflation ended properly. The universe was supposed to transition from rapid inflation to normal expansion, converting the inflaton field's energy into particles. But Guth's original mechanism didn't work. The problem was reheating, or rather the lack of it. Guth's model relied on something called bubble nucleation. The inflaton field existed in a high-energy state he called false vacuum, like a ball balanced on a hilltop. Eventually, the field would tunnel through to a lower energy state called true vacuum, like the ball rolling down into a valley. This transition would release enormous energy, reheating the universe and creating matter. In Guth's picture, bubbles of true vacuum would form randomly in the sea of false vacuum. Each bubble would expand at light speed. When bubbles collided, they would release energy and create particles. The universe would heat up through these collisions. But here's what went wrong. If inflation lasted long enough to solve the horizon and flatness problems, the bubbles became incredibly rare. Space expanded so fast that bubble formation couldn't keep up. In any observable region, only one bubble would form, if any. There would be no collisions, no energy release, and no reheating. The universe would remain cold and empty forever. Think of it like raindrops forming in a storm, but the clouds expand faster than rain can form. The drops become so spread out that they never hit each other or the ground. You end up with a vast, dry sky despite the presence of moisture. Guth realized this problem immediately. He published his paper anyway, hoping someone would find a solution. The idea of inflation was too powerful to abandon over a technical difficulty. Within a year, André Linde and others developed a fix. Instead of bubbles nucleating abruptly, they proposed that the inflaton field could roll slowly down from high energy to low energy, like a ball rolling gently down a hill rather than suddenly appearing at the bottom. This process, called slow roll inflation, avoided the bubble problem entirely. In slow roll inflation, the field doesn't transition through quantum tunneling. It just gradually decreases in energy as the field evolves according to its equations of motion. When the field reaches low enough energy, it oscillates rapidly and decays into particles. This happens smoothly throughout space, not just in localized bubbles. Reheating occurs everywhere simultaneously. This version of inflation works. It solves the original problems Guth identified while also successfully reheating the universe. It's become the standard picture of how inflation operated. But the story illustrates something important about theoretical physics. Ideas often start flawed. The first version of a theory rarely works perfectly. Scientists identify problems, propose fixes, and gradually refine the idea until it matches observations. Inflation survived its initial failure because the core concept was valuable enough to deserve repair. Today, inflation theory continues evolving. Physicists propose dozens of different inflation models with different field properties and different predictions. Some involve multiple fields. Some have complex energy landscapes. Some connect to string theory or quantum gravity. No single inflation model has been proven correct yet. The data we have narrows the possibilities, but doesn't uniquely identify one mechanism. Future observations might finally pin down exactly how inflation worked. Until then, we know inflation happened, but the details remain mysterious. The seeds of every galaxy in existence began as random quantum jitters smaller than an atom. Quantum mechanics tells us that nothing is ever truly still. Even in perfect vacuum, fields fluctuate randomly at microscopic scales. These fluctuations are tiny, lasting for infinitesimally short moments before disappearing. They're the universe's way of being uncertain at the smallest scales. Normally, these quantum jitters have no lasting effect on anything large. But during inflation, something extraordinary happened. As space expanded exponentially, quantum fluctuations in the inflaton field got stretched. A fluctuation that started smaller than a proton grew to the size of a galaxy, then a galaxy cluster, then even larger. The expansion happened so fast that the fluctuations didn't have time to smooth out or disappear. They froze in place, becoming permanent features of the cosmic landscape. Think of it like taking a photograph of ripples on water. The ripples are temporary and would normally fade away, but if you freeze them in a picture, they become permanent. Inflation did something similar to quantum fluctuations, freezing them into the structure of space itself. These frozen fluctuations became density variations in the early universe. Some regions had slightly more energy than average. Others had slightly less. The differences were tiny, about 1 part in 100,000, but they were enough. When inflation ended and matter formed, gravity amplified these tiny differences. Regions that were slightly denser had stronger gravity, pulling in more matter. Regions that were slightly less dense lost matter to their denser neighbors. Over millions and billions of years, these tiny seeds grew into the cosmic web we observe today. Every galaxy exists because of a quantum fluctuation during inflation. Every galaxy cluster, every supercluster, every void traces back to random quantum noise magnified to cosmic proportions. The universe's largest structures have the smallest possible origin. This is confirmed by observations. The cosmic microwave background shows the pattern of hot and cold spots that correspond exactly to these frozen quantum fluctuations. The statistical properties of those spots match what we'd expect from quantum mechanics. The universe's structure follows quantum rules scaled up to astronomical size. Scientists can even calculate the exact spectrum of fluctuations inflation should produce. The power spectrum, as it's called, describes how much variation exists at different scales. Inflation predicts a nearly scale-invariant spectrum, meaning fluctuations have similar strength whether they're galaxy-sized or supercluster-sized. Observations confirm this prediction. The connection between quantum mechanics and cosmology is one of the most profound insights in physics. The smallest and largest scales of nature aren't separate. They're linked through inflation. What happens at subatomic scales determines the structure of the entire observable universe. But this raises deep questions about randomness and determinism. If galaxy locations depend on random quantum fluctuations, then the universe's structure is fundamentally probabilistic. There's no deeper reason why galaxies formed where they did. It's just quantum chance, amplified and frozen. Some physicists find this troubling. Others find it beautiful. The universe's grandest structures emerged from pure randomness, given form by the laws of physics acting over cosmic time. Either way, every star you see exists because of quantum uncertainty. The cosmic microwave background has strange patterns in its temperature that shouldn't be there. When scientists analyze the cosmic microwave background, they break it down into components called multipoles. These describe temperature variations at different angular scales across the sky. Low multipoles represent large-scale patterns. High multipoles represent small-scale patterns. The Standard Model predicts how strong each multipole should be based on inflation and cosmic evolution. Most multipoles match predictions perfectly, but some don't. The Quadrupole, which describes the largest scale temperature pattern, is unexpectedly weak. The Octupole, the next scale up, shows strange alignment with the ecliptic plane, the flat disk of our solar system. This alignment makes no sense. The cosmic microwave background formed billions of years before our solar system existed. There should be no relationship between them. These are confirmed anomalies, not measurement errors, though their statistical significance remains debated. The quadrupole problem means the universe has less large-scale temperature variation than expected. Think of it like measuring sound waves and finding that the deepest bass notes are quieter than they should be. The physics that generated all the other frequencies should have generated strong bass too, but it didn't. Several explanations have been proposed. Maybe inflation lasted slightly longer than the Standard Model assumes, erasing some large-scale fluctuations. Maybe the universe has some large-scale structure beyond what we can observe, affecting how we perceive patterns within our observable patch. Maybe there's new physics that suppresses fluctuations at large scales. The alignment with the ecliptic is even stranger. The octupole and quadrupole both show preferential orientation toward the plane of our solar system. This was first noticed by the Cosmic Background Explorer satellite in the early 90s, then confirmed by subsequent missions. It's been nicknamed the Axis of Evil because it seems to violate the cosmological principle that the universe should look the same in all directions. Some scientists think this is just statistical fluke. When you analyze complex data, occasionally you find patterns that look meaningful but are actually random. The human brain is very good at seeing patterns, even in noise. Maybe we're overinterpreting random alignments. Others think it's real evidence for something beyond the Standard Model. Maybe the universe has some preferred direction. Maybe our observable patch sits inside a larger structure with its own orientation. Maybe the cosmological principle is wrong and the universe isn't truly isotropic. Loop quantum cosmology offers one explanation. This theory, which applies quantum mechanics to the entire universe, predicts that the universe might have bounced rather than starting from an absolute singularity at the Big Bang. The bounce would leave imprints in the large-scale structure, potentially explaining the multipole anomalies. The bounce idea says the universe was contracting before the Big Bang reached a minimum size, then rebounded and started expanding. During the contraction phase, quantum effects became important, preventing the universe from collapsing to zero size. The rebound launched the expansion we observe today. If this happened, the quantum state during the bounce would correlate large-scale modes in ways that standard inflation doesn't predict. The quadrupole suppression and the peculiar alignments could be echoes of the pre-bounce universe. This is speculative, not confirmed, but it shows how anomalies drive new theories. When observations don't match predictions, physicists develop new models that might explain the mismatch. Sometimes the anomalies fade with better data. Sometimes they lead to revolutionary insights. The multipole anomalies remain puzzling more than 2 decades after their discovery. A fundamental frequency in the universe's temperature is far weaker than physics predicts. Imagine listening to an orchestra where all the instruments play beautifully, except the bass section, which is barely audible. You'd wonder what happened to the bass. Did the instruments break? Is something absorbing those frequencies? The cosmic microwave background faces this exact puzzle. The quadrupole represents temperature variations on the largest angular scales we can measure. It should be strong because inflation generates fluctuations at all scales with similar power. The models predict a certain amplitude for the quadrupole based on how smaller scale fluctuations behave. But when we measure it, the quadrupole comes in significantly weaker. This discrepancy has survived decades of scrutiny. COBE found it, WMAP confirmed it, Planck verified it with even better precision. The quadrupole is genuinely weak, about 30% below predictions. Here's why this matters beyond just one anomalous measurement. The quadrupole corresponds to the largest observable structures in the universe. If it's weak, That means the universe has less variation on the largest scales than expected. This could be telling us something profound about how inflation ended, or about the geometry of space beyond what we can observe. One possibility is that inflation didn't last quite long enough to generate strong fluctuations at the very largest scales. If inflation ended just a bit earlier than assumed, the modes that would become the quadrupole might not have fully developed. They'd still exist, but would be suppressed compared to smaller scales. Another possibility involves cosmic topology. What if the universe wraps around on itself like the surface of a hypersphere? If the universe is finite rather than infinite, then the largest possible fluctuations are limited by the universe's total size. A weak quadrupole could indicate that we're seeing the edge of possibility, where the universe simply doesn't have room for larger variations. Think of it like waves in a bathtub versus waves in an ocean. The bathtub limits how long the waves can be. The ocean allows much longer wavelengths. If the universe is more like a bathtub than an ocean, the longest wavelength fluctuations would be suppressed. Some researchers have explored whether we're living in a closed universe with a radius only slightly larger than our observable region. This would naturally explain the weak quadrupole, but other observations suggest the universe is flat, not closed, making this explanation problematic. The weak quadrupole might also connect to the Hubble tension and dark energy mysteries. If something unusual happened in cosmic history that affected expansion, it could also affect how large-scale fluctuations evolved. Maybe early dark energy or time variations in the expansion rate left an imprint on the quadrupole. No explanation has gained consensus yet. The weak quadrupole remains one of several small puzzles in the cosmic microwave background that don't quite fit the standard model. Individually, each anomaly could be a fluke. Collectively, they suggest something interesting might be happening that our current theories don't capture. Future observations will either confirm these anomalies as real signals requiring new physics or reveal them as statistical noise that fades with more data. For now, the bass section of the cosmic orchestra plays inexplicably quiet. Empty regions of space exist that are so large they shouldn't be possible, according to standard cosmology. In 2007, astronomers found something disturbing. A void in space nearly 1 billion light-years across, far larger than any structure the standard model says should exist by that time in cosmic history. They called it the cold spot supervoid because it corresponds to an unusually cold region in the cosmic microwave background. But here's the issue. Structures take time to form through gravity. After the Big Bang, matter was nearly uniform. Small density variations grew slowly as gravity pulled matter together. By the time the universe was a few billion years old, structures shouldn't have reached such enormous sizes. Yet supervoids exist. Multiple have been found since that first discovery. These aren't just empty regions. They're organized structures where galaxies cluster around the edges while the interior remains remarkably empty. The formation process requires coordinated gravitational dynamics over vast regions. Think of it like finding a massive canyon on a young planet. Canyons take millions of years to form through erosion. If you find one on a planet only a few thousand years old, something is wrong with your understanding of either the planet's age or how canyons form. Supervoids present the same problem for cosmology. They exist, but standard models struggle to explain how they formed so quickly. One proposed explanation involves dark energy. If dark energy's strength varied across space, regions with stronger dark energy would expand faster, creating voids. But standard dark energy is supposed to be uniform, the same everywhere. Varying dark energy requires new physics. Another explanation suggests these structures aren't actually as large or problematic as they seem. Maybe our distance measurements are slightly off, making the voids appear bigger than they really are. Or maybe we're just getting unlucky, observing rare statistical outliers that happen to be larger than average. The timescape model, which treats the universe as lumpy rather than smooth, might also explain supervoids naturally. If expansion varies across different regions, with voids expanding faster than average, then supervoids could grow larger than uniform expansion allows. The structures form through the interplay of varying expansion rates rather than gravity alone. This connects to the broader question of whether we can treat the universe as smooth on large scales. Standard cosmology assumes yes. The cosmic web is just small-scale structure sitting atop a smooth background expansion. But if the web itself affects expansion in important ways, then our smooth universe models miss crucial physics. Supervoids might be telling us that lumpiness matters more than we thought. The universe isn't a smooth fluid that happens to have galaxies sprinkled in. It's a genuinely structured cosmos where the distribution of matter affects how space expands. Future galaxy surveys will map more of the cosmic web, revealing how common supervoids are and how large they can grow. If they're everywhere and consistently larger than models predict, that's strong evidence for new physics. If they turn out to be rare edge cases, the standard model survives. The challenge is understanding what we're seeing. Are supervoids mundane features that just look strange, or are they signposts pointing toward deeper truths about dark energy and cosmic expansion? The answer affects how we interpret everything else about the universe's structure. The most powerful telescope ever built just made the expansion problem worse instead of solving it. When James Webb Space Telescope launched in December 2021, many scientists hoped it would resolve the Hubble tension. Webb's unprecedented infrared vision should reveal details about distant galaxies and stars that earlier telescopes missed. If measurement errors caused the tension, Webb would find them. The crisis would fade. That's not what happened. In 2024, Adam Rees and his team published Webb's observations of Cepheid variable stars in distant galaxies. These pulsating stars act as cosmic yardsticks, allowing precise distance measurements. Webb can see them more clearly than Hubble ever could, reducing uncertainties and improving accuracy. Webb's results matched Hubble's almost exactly. The expansion rate came out at 73 kilometers per second per megaparsec, confirming the higher local measurements. The hope that Hubble had subtle systematic errors died with Webb's confirmation. But Webb did more than confirm Hubble. It extended measurements to more distant galaxies, farther up the cosmic distance ladder. Every new data point agreed with the pattern Hubble established. The universe expands faster locally than predictions from the early universe allow. This is real, not an artifact of measurement problems. Some scientists had speculated that stellar crowding might bias Hubble's measurements. When you look at distant galaxies, individual stars blur together. If brighter stars happen to overlap with Cepheid variables, you might misjudge their true brightness and calculate wrong distances. Webb's sharper vision should reveal this if it's happening. It's not happening. Webb can resolve individual stars better than Hubble, and the distances don't change. Stellar crowding isn't hiding a systematic error. The measurements really are correct. This pushes the problem from observations to theory. Measurements aren't wrong. The mismatch between early and late universe expansion is genuine. Something about our understanding of cosmic evolution must be incomplete. Rees, who won a Nobel Prize for discovering accelerating expansion in 1998, stated it clearly. With measurement errors ruled out, the exciting possibility remains that we've misunderstood the universe. New physics might be necessary. Webb also observed extremely distant galaxies from the universe's first billion years. These observations revealed more bright, massive galaxies than the standard model predicts should exist so early. The universe seems to have made large structures faster than our theories say is possible. This ties to the early dark energy hypothesis. If a temporary burst of dark energy accelerated the universe briefly during its first 100,000 years, that would allow structures to form faster. It would also affect expansion in ways that resolve the Hubble tension. Both problems might have the same solution. Webb will continue observing for years, building up enormous data sets that will test these ideas. But the first results already point clearly toward new physics. The standard model explains most of cosmic history remarkably well, but it's missing something important about how the universe expanded. Within a decade, Webb combined with other next-generation telescopes should reveal what that missing piece is. For now, the crisis intensifies with every new observation. Empty space has energy, but the amount makes no sense according to particle physics. Dark energy is often described as the energy of empty space itself, a property of vacuum. Quantum field theory, our best theory of particle physics, predicts that vacuum should indeed have energy. Particles and antiparticles constantly pop in and out of existence in brief quantum fluctuations. These virtual particles contribute energy to the vacuum. Here's the catastrophic problem. When physicists calculate how much energy the vacuum should have based on quantum field theory, they get an absurdly large number. The calculation predicts the vacuum energy should be about 10 to the power of 120 times larger than what we observe. That's not a small error. That's the worst prediction in the history of physics, off by 120 orders of magnitude. Think of it like predicting someone's height will be 1 inch and finding they're actually tall enough to stretch from Earth to the edge of the observable universe and back trillions upon trillions of times. The prediction isn't just wrong, it's catastrophically, unimaginably wrong. If the vacuum energy were as large as quantum field theory predicts, the universe would have blown apart instantly after the Big Bang. Space would expand so violently that atoms couldn't form. No stars, no galaxies, no structure of any kind could exist. Yet here we are, in a universe that clearly has much, much less vacuum energy than theory predicts. Why is the actual value so tiny compared to the prediction? Nobody knows. This is called the cosmological constant problem, and it's one of the deepest mysteries in theoretical physics. Some physicists think quantum field theory must be wrong about vacuum energy. Maybe the virtual particles don't contribute the way we calculate. Maybe there's a mechanism that cancels out most of the vacuum energy, leaving only the small amount we observe. But nobody has found a convincing mechanism. Others think we're missing something about how quantum mechanics and gravity work together. Our calculations use quantum field theory in flat space, but the universe's space is curved by gravity. Maybe the calculation breaks down when you properly account for gravity. Quantum gravity, if we ever figure it out, might solve the problem. Supersymmetry, a theoretical extension of particle physics, was once hoped to solve this. Supersymmetry predicts that every known particle has a heavier partner particle. The contributions from particles and their superpartners should cancel exactly, leaving zero vacuum energy. But experiments at the Large Hadron Collider haven't found any superpartner particles yet, and the theory is looking less promising. Another idea is the anthropic principle. Maybe the vacuum energy takes different values in different regions of a vast multiverse. Most regions have huge vacuum energy and can't support life. We exist in one of the rare regions with tiny vacuum energy, simply because that's the only place where observers like us could evolve. This explains the observation but doesn't feel satisfying. It replaces a physics explanation with a selection effect. The problem matters because dark energy dominates the universe's energy budget. Understanding why it has the value it does would reveal something fundamental about the laws of physics. It might connect quantum mechanics to gravity. It might tell us about physics at the highest energy scales. It might even reveal that our universe is part of a multiverse. For now, the cosmological constant remains one of the biggest unsolved problems in physics. The universe's expansion depends on it, but we have no idea why it exists or why it has the value it does. What if Einstein's equations work perfectly in our solar system but break down across cosmic distances? General relativity has passed every test we've thrown at it. It predicts the orbit of Mercury, the bending of starlight around massive objects, gravitational waves from colliding black holes, and the time dilation experienced by GPS satellites. Within our solar system and around nearby stars, Einstein's theory works flawlessly, but maybe it fails at larger scales. Maybe gravity behaves differently when you reach distances of millions or billions of light years. This isn't as crazy as it sounds. Modified gravity theories propose that Einstein's equations are approximately correct but need additional terms that only matter at cosmic scales. These extra terms could affect how the universe expands without requiring dark energy. The acceleration we observe might not come from mysterious energy pushing space apart. It might come from gravity itself behaving differently than Einstein predicted. One approach is called MOND, Modified Newtonian Dynamics, though more sophisticated relativistic versions exist. These theories add corrections to gravity that become important when accelerations are extremely tiny, far smaller than anything we experience on Earth, but relevant for the outskirts of galaxies and beyond. The motivation comes from galaxy rotation curves. Galaxies spin faster than they should based on their visible matter. Standard physics explains this with dark matter, invisible mass that provides extra gravity. But modified gravity explains it by changing the law of gravity. Maybe both dark matter and dark energy are illusions created by our incomplete understanding of how gravity works. The challenge for modified gravity theories is explaining everything that dark matter and dark energy explain. Dark matter fits observations from galaxy scales to the cosmic microwave background. Dark energy explains not just acceleration but also precise details of the universe's expansion history. Any alternative theory has to match all those successes. Some modified gravity theories succeed in certain regimes but fail in others. They might explain galaxy rotation without dark matter, but can't explain gravitational lensing observations. Or they might explain acceleration without dark energy, but predict a cosmic microwave background pattern that doesn't match what we observe. Recent versions of modified gravity are more sophisticated. They incorporate screening mechanisms that make the modifications turn off in dense regions like our solar system, allowing them to pass local tests while still affecting cosmic expansion. These theories are hard to distinguish from dark energy observationally because they're designed to mimic dark energy's effects. Testing modified gravity requires looking for subtle differences in how structure grows over cosmic time. Dark energy simply pushes space apart. Modified gravity changes how matter clusters under its own gravity. These effects differ slightly, and next-generation surveys should be able to tell them apart. The DESI results showing possible evolution in dark energy could also fit some modified gravity models. If gravity's strength changes over cosmic time, that would affect expansion in ways that look like evolving dark energy. Einstein himself added a cosmological constant to his equations to make the universe static, then called it his greatest blunder when Hubble discovered expansion. Now we know the constant might actually exist as dark energy. But maybe the real lesson is that Einstein's original equations, even with the constant, aren't quite right at the largest scales. The stakes are enormous. If gravity needs modification, that revolutionizes physics. If gravity is correct and dark energy is real, we need to understand what dark energy is and where it comes from. Either way, something profound is waiting to be discovered. Two types of stars, used to measure cosmic distances, give conflicting results, deepening the crisis. Cepheid variable stars have been the gold standard for measuring cosmic distances for over a century. These stars pulse regularly, brightening and dimming with periods ranging from days to months. The period correlates precisely with the star's true brightness. Measure the period, calculate the true brightness, compare it to observed brightness, and you get the distance. Adam Rees's team has used Cepheids extensively, building the cosmic distance ladder that gives an expansion rate of 73. Their measurements are meticulous, cross-checked, and confirmed by Webb Space Telescope. The Cepheid calibration appears solid, but Wendy Friedman's team argues for a different approach, using red giant stars. These are aging stars that have exhausted hydrogen in their cores and expanded to enormous size. As they evolve, they reach a maximum brightness before transitioning to helium burning. This maximum brightness, called the tip of the red giant branch, is remarkably uniform. Red giants make excellent standard candles. Friedman's team published results in 2024 using red giant measurements from Webb and Hubble. Their expansion rate came out around 70, lower than Rees's 73 but higher than Planck's 67. This splits the difference. suggesting the Hubble tension might not be as severe as Rees claims. This disagreement isn't about competence or carefulness. Both teams are world-class, meticulous about systematics, and transparent about their methods. They're using different stars as calibrators and getting different answers. Someone is right, or both are missing something subtle. The controversy centers on which stars make better calibrators. Cepheids are brighter, allowing measurements to more distant galaxies, but they're complicated. Young Cepheids behave differently from old Cepheids. Metallicity affects their brightness. Extinction from dust can bias measurements if not corrected properly. Red giants are simpler in some ways. The tip of the red giant branch is a clean physical transition that happens at a well-defined brightness. But red giants are dimmer than Cepheids, limiting measurements to nearby galaxies, and identifying exactly which stars are at the tip requires careful analysis. Rees's team argues that Friedmann's sample of Type 1a supernovae used for calibration is too small, potentially introducing bias. Friedmann's team counters that Rees's Cepheid calibrations have hidden systematics that haven't been fully accounted for. This disagreement matters because it determines whether the Hubble tension is a crisis requiring new physics or a measurement problem that careful work can resolve. If Cepheids give 73, and that's correct, the tension with 67 is enormous. If red giants give 70, and that's correct, the tension shrinks significantly. Some researchers have tried using completely independent calibrators to break the tie. Gravitational lensing, where massive objects magnify background galaxies, provides distance measurements that don't rely on standard candles. These measurements tend to favor higher expansion rates, closer to 73 than 67. Other methods using mirror variable stars or water mazes in distant galaxies also tend toward higher values. The preponderance of evidence leans toward Rees's higher number, but Friedmann's concerns about systematics remain valid. Future observations with Webb will help. The telescope can observe both Cepheids and red giants in the same galaxies, allowing direct comparison. If both methods give the same distances, one set of calibrators is being used incorrectly. If they continue to disagree, something deeper might be wrong with our understanding of stellar evolution. The calibration war continues, with the fate of cosmology hanging on which stars we trust. The exploding stars we use as cosmic measuring sticks might not be as standardizable as we thought. Type 1a supernovae happen when white dwarf stars accumulate enough mass to trigger runaway nuclear fusion. The explosion destroys the star completely, releasing energy in a remarkably consistent way. This consistency makes them perfect for measuring cosmic distances. Observe a Type 1a supernova, measure its brightness, and you know how far away it is. These supernovae were used to discover accelerating expansion in 1998. They remain the primary tool for measuring the universe's expansion at moderate distances. The entire cosmic distance ladder depends on them, but recent observations reveal complications. Not all Type 1a supernovae are identical. Some are slightly brighter or dimmer than average. Some fade faster or slower. The variations are small but not negligible when you're trying to measure expansion to 1% accuracy. Astronomers have developed sophisticated techniques to standardize these supernovae. They correct for the brightness-decay rate correlation. They account for color differences. They calibrate against nearby supernovae, whose distances are known from other methods. After corrections, Type 1a supernovae become excellent standard candles. But what if the corrections themselves introduce systematic errors? What if the way supernovae explode has changed subtly over cosmic history? Stars in the distant past had different chemical compositions than modern stars. Less heavy elements means different explosion dynamics. These differences could bias distance measurements in ways we don't fully understand. Some researchers worry about dust. Light from supernovae travels through interstellar and intergalactic space before reaching us. Dust can absorb and scatter light, making supernovae appear dimmer and therefore farther away. We correct for dust absorption using color measurements, but those corrections rely on assumptions about what kind of dust exists. If distant galaxies have different dust properties than nearby galaxies, our corrections fail. We'd systematically overestimate distances to distant supernovae, making the universe appear to be expanding faster than it really is. The acceleration might be partially or entirely an artifact of incorrect dust corrections. Other complications involve the progenitor systems. We're not entirely sure how Type 1a supernovae form. The traditional picture involves a white dwarf accreting matter from a companion star until it reaches critical mass. But some supernovae might result from two white dwarfs merging. These different formation channels could produce supernovae with slightly different properties. Detailed studies suggest these effects are small, not large enough to explain away the Hubble tension entirely, but they add uncertainty. Every additional source of systematic error makes the measurements less reliable. The good news is that independent methods now confirm the supernova results. Gravitational lensing, Cepheid variables, and red giant stars all point towards similar expansion rates. If supernovae had huge systematic errors, the other methods wouldn't agree. The consistency suggests the supernova measurements are fundamentally sound, but small biases could still exist. Shaving even 0.5% off the measured expansion rate would ease the Hubble tension slightly. Confirming that supernovae are truly reliable requires understanding them better. That means observing more supernovae, studying their host galaxies, and modeling the explosion physics in greater detail. Webb Space Telescope is now observing supernovae in the early universe, when cosmic conditions were very different from today. These observations will test whether supernovae behave consistently across cosmic time. If early supernovae look systematically different, we'll need to revise our distance measurements and maybe our conclusions about dark energy. The rulers we've been using to measure the universe might need recalibration. A new measurement using a nearby galaxy cluster just pushed the expansion rate even higher than before. Dan Skolnick's team published their latest results in January 2025, and the number shocked the cosmology community. 76.5 kilometers per second per megaparsec. That's higher than any previous reliable measurement. It's not just confirming the Hubble tension, it's intensifying it. The measurement used the Coma cluster, a large group of galaxies only 320 million light-years away. This is our cosmic backyard, close enough to measure distances with exceptional precision. The team observed Type 1a supernovae in galaxies within the cluster, calibrating distances carefully. The Coma cluster has been studied for decades. Its distance was already well constrained by multiple independent methods. Using it as the first rung of the distance ladder grounds the measurement in solid, nearby observations rather than relying on long chains of calibrations that accumulate uncertainty. The result is robust. The team checked for every possible systematic error. They varied their analysis methods. They used different supernova samples. The answer kept coming back around 76. This isn't a fluke or a mistake. It's a genuine measurement. What makes this significant is that it's independent of the Cepheid controversy. Friedman and Rees disagree about whether to use Cepheids or red giants for calibration. Skolnick's measurement bypasses that debate entirely by starting with a nearby cluster whose distance we know from multiple methods. The higher expansion rate emerges regardless of stellar calibration issues. This eliminates one possible escape hatch from the Hubble tension. If the tension came from problems with Cepheid calibration, then measurements not using Cepheids should give different results. They don't. The high expansion rate appears real. 76.5 compared to 67 is a 13% discrepancy. That's enormous in cosmology. Imagine two teams measuring the age of Earth and one getting 4.5 billion years while the other gets 3.9 billion. Both can't be right. Something fundamental is wrong. The tension now qualifies as a crisis by any reasonable standard. It's not going away with better measurements. It's getting worse. Every new, more precise observation makes the discrepancy larger and harder to dismiss. This forces a reckoning. Either measurements from the early universe are wrong, or measurements from the nearby universe are wrong, or our theory connecting the two is wrong. Measurements appear sound, the instruments work, the methods are validated, so the theory must be incomplete. The standard model of cosmology assumes dark energy is constant and space expands uniformly according to Einstein's equations. Maybe dark energy isn't constant. Maybe it evolved over time or varies across space. Maybe Einstein's equations need corrections at cosmic scales. Maybe the universe's lumpiness affects expansion more than we account for. All these possibilities are now on the table, taken seriously by researchers trying to resolve the crisis. Within a few years, data from Euclid, Roman, and continued observations from Webb should narrow the options. We'll either find new physics that explains the tension or discover a subtle systematic error everyone missed. But right now, with the data we have, the universe expands faster than our best theories predict it should. And nobody knows why. The answers could rewrite everything we understand about reality. This isn't hyperbole. The expansion rate of the universe determines its age, its fate, and the validity of fundamental physics theories. If we're wrong about expansion, we might be wrong about dark energy, dark matter, inflation, or even general relativity itself. The implications spread through all of cosmology and into particle physics. Here's what the next decade will bring. The Euclid satellite is already mapping the cosmic web with unprecedented detail. It will measure how galaxies cluster and how that clustering has evolved over billions of years. Different expansion histories produce different clustering patterns. Euclid will distinguish between constant dark energy, evolving dark energy, modified gravity, and the timescape model. NASA's Roman Space Telescope launches in 2027. It will observe thousands of supernovae across cosmic history, tracing the expansion rate with precision no previous mission could match. Roman will also study gravitational lensing, providing independent distance measurements that don't rely on supernovae or Cepheids. Ground-based observatories, like the Vera Rubin Observatory, will survey billions of galaxies, creating three-dimensional maps of cosmic structure. These maps will reveal whether supervoids are common or rare, whether expansion varies across different regions, and whether time dilation in voids matters enough to explain the acceleration without dark energy. DESI will continue its survey, eventually mapping 40 million galaxies. With that enormous dataset, the hints of evolving dark energy will either strengthen into confirmed detection or fade into statistical noise. We'll know within 5 years whether dark energy is truly changing. Webb will keep observing early galaxies, testing whether structures formed faster than standard models predict. Combined with measurements of the cosmic microwave background from ground-based experiments like the Simons Observatory, will constrain whether early dark energy existed and affected cosmic evolution. All these missions together will determine which possibility is correct. Maybe dark energy is constant, and we've been making subtle measurement errors. Maybe dark energy evolves, and we need new physics to explain why. Maybe dark energy doesn't exist, and the timescape model is correct. Maybe gravity needs modification at cosmic scales. Each possibility leads somewhere profound. If dark energy is real and constant, we need to understand why empty space has energy and why the amount is so much smaller than particle physics predicts. That connects cosmology to quantum mechanics in ways we don't currently understand. If dark energy evolves, we need to identify the physical mechanism driving that evolution. It might be a field like the inflaton, a new fundamental force, or a signature of extra dimensions. Discovering it would reveal physics beyond the standard model. If dark energy doesn't exist and the timescape model is right, we've spent 27 years chasing an illusion created by treating a lumpy universe as smooth. That would be embarrassing but also liberating. No need to explain mysterious energy, just better accounting for how structure affects expansion. If gravity needs modification, Einstein's greatest triumph has limits. General relativity would be approximately correct. like Newtonian gravity is approximately correct, but incomplete at the largest scales. A deeper theory of gravity is waiting to be discovered. We're at a moment similar to the late 1800s, when physicists thought they understood physics but had a few nagging problems. Those problems led to relativity and quantum mechanics, completely revolutionizing science. The Hubble tension might be our generation's nagging problem that leads to revolution. The universe is telling us something. Expansion doesn't make sense according to our current understanding. That's not a failure. It's an opportunity. Nature is handing us a puzzle whose solution will deepen our knowledge of reality itself. The mystery is almost solved. The data is arriving. The instruments are working. Within a decade, we'll know why the universe's expansion doesn't make sense according to our theories. And knowing that will change everything.